we'll take a look at deep convolutional generative adversarial networks. We'll start off by taking a look at generational adversarial networks and deep convolutional variants, and then we'll implement a deep convolutional generative adversarial network model with PyTorch. We'll actually train and evaluate it on a data set, and then finally we'll take a look at what it takes to improve performance. First, let's take a look at the result of the assignment from the last section. You can actually see here I'm actually working with roughly the same code that was the final model, but I made a couple of changes. I actually changed the size and I actually added layers and dropout with a GRU rather than an LSTM. So what this is effectively doing is stacking 4 GRUs together with that layer argument with a little bit of dropout. Again, I'm actually taking the hidden output, which is the final vector, and then stacking it through, and I ran a lot of training loops. I ran 128 iterations. And you can actually see over here the training results. The loss goes from relatively large value down to relatively small values at the end, and it's actually a pretty good loss when it's overall said and done, 0.0049 through 128 training loops. And then at the bottom, I've actually got the results of the classification report. You can actually see that we've got a pretty good improvement down to a 44%. Now in this video, we'll take a look at an introduction to generative adversarial networks and the deep convolutional variant. We'll look at the difference between classification, regression, and generation. We'll ask what is a generational adversarial network, what is a deep convolutional generational adversarial network, and then talk a little bit about how you train these networks. So basically, classification takes data and it assigns labels or classes. This is the classic yes or no, or 0 to 5 scoring, or is it a car or a bird or a plane. Regression takes data and generates a real valued number to a tensor, like what we worked with on property values to predict the dollar price of a house. Now generation is a different thing. It actually takes random inputs, so not really data. It takes a random set of inputs and it actually generates data. So you can think of generational networks as essentially neural networks in reverse. But instead of labeling data, what we're actually looking to do is build data. Diagram of a deep generational network about how it works, particularly when generating image data. So you actually start off with a relatively small vector, say you have like 100 elements. Then you actually do a transposed convolution. So instead of convolving to actually reduce dimensions, you actually convolve to increase the number of dimensions. So you can see here we go from a 4x4 image to an 8x8 image to a 16x16 to a 32x32 to a 64x64. And at each step, the convolution is actually projecting a depth. So a depth in terms of a number of features, and then it's going to a slightly narrower depth. So what we're doing is we're taking a vector of 100 and we're actually making it wider in terms of the x and y and shallower at each iteration until we finally end up with an image that is roughly our target size, in this case 64x64, with our target number of color channels. So how do you actually train these things? Well, you can actually classify real data with a discriminator, and that's actually a network that tells you, is this real data or is this fake data from the generator? And then you generate fake data with a network generator. So you do have random data inputs and you generate fake data. And then in each step of the training loop, you try to fool the discriminator by having it classify data from the generator. And so the goal of the discriminator is to learn the difference between real and fake data. And the goal of the generator is to generate data that looks enough like the real data that it actually fools the discrimination network. And so why would you do this? Well, these generational networks form a set of unsupervised models and are useful to generate interesting test data as well as for pre-training and transfer learning to learn representations of what is or is not. The good news is, in order to use these, you don't actually have to have labeled data at all. You can use pretty much any kind of data and generate similar or lookalike data with a different network. It's adversarial because there's two networks. The discriminator and the generator are actually, in a sense, competing with one another to establish an equilibrium in an overall game. And the discriminator's job is to say, is this real or not? And the generator's job is to generate data that looks real enough to actually fool the network. It's actually a very clever technique, and there have been a lot of interesting applications of this, including generating synthetic people as well as artwork from computers.